There is a square in Rome, Campo de Fiori, the field of flowers. Right at its center stands a bronze figure in a monk's robe, its face cast downward, hidden in shadow. His name was Giordano Bruno, and in the year 1600, on the 17th of February, the church lit a fire beneath his feet on that very square, because he refused to stop saying what he believed to be true. What did he say? He said the universe has no center. He said the stars are not holes in a celestial dome. They are other suns, impossibly far away. And he said something that people in his time considered outright delirium, that space extends forever, infinitely in every direction, and that somewhere out there, infinitely far from here, there are other Earths, other lives, other worlds indistinguishable from this one. He was not a scientist in the modern sense. He was a philosopher and a mystic, but the idea he planted in 1584 in his treatise on the infinite universe and worlds turned out to be, 4 centuries later, a legitimate and deeply unsettling question of mathematical cosmology. And here is where we need to sit with something uncomfortable. Right now, at the start of this video, if the universe is truly infinite, and if matter is distributed throughout it in any way that is not perfectly, impossibly ordered, then somewhere out there, right now, there is a version of this room, a version of you, reading or hearing these exact words, living through this exact moment. Let us start with scale, because our intuition is hopelessly broken when it comes to big numbers. The observable universe, the bubble of space from which light has had time to reach us since the Big Bang, has a diameter of roughly 93 billion light years. That number is already beyond anything our nervous systems were built to grasp. It contains somewhere between 100 billion and 2 trillion galaxies, each holding hundreds of billions of stars. But here's the critical word: observable. The observable universe is not the universe. It is the universe as seen from here, limited by the speed of light and the age of time. The full universe, if it is infinite, extends arbitrarily far beyond that boundary. We cannot see it. We cannot directly measure it, but we can ask whether the physics we do know permits it, even demands it. And here is the uncomfortable answer: yes. The most precise measurements we have, from the Planck satellite's mapping of the cosmic microwave background, the faint afterglow of the Big Bang, indicate that space on the very largest scales we can probe is flat, not curved like the surface of a sphere, not saddle-shaped, flat, to within less than 1% of measurement error. And a universe that is spatially flat and consistent with standard inflationary cosmology is either infinite or so enormously larger than what we can see that the distinction barely matters. Is this actually a scientific claim, or is it just philosophy dressed in mathematics? We will come back to that. But first, let us think about what infinity actually does to probability. In the 1920s, the German mathematician David Hilbert gave a series of lectures in which he described a thought experiment that has haunted mathematicians ever since. Imagine a hotel with infinitely many rooms. Room 1, room 2, room 3, and so on, forever. The hotel is full. Every room is occupied. And yet, a new guest arrives. No problem, says the manager. We simply ask every current guest to move from their room to the room with the next higher number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. And room 1 becomes free. Infinitely many guests shifted, and we created a new vacancy out of nothing. It gets stranger. An infinitely large bus arrives. Infinitely many new guests. Still no problem. Every current guest moves from room number n to room number 2 times n. Odd-numbered rooms, infinitely many of them, suddenly become available. The hotel absorbs an infinite crowd without adding a single room. Hilbert's hotel is not a riddle about hotels. It is a demonstration that infinity does not behave like a very large number. Infinity is a fundamentally different category. And once you accept that, once you let it sink in, the implications for a physically infinite universe become deeply strange. In an infinite universe, every finite pattern of matter, every arrangement of atoms must repeat, not because of some mystical law, but because there are only finitely many ways to arrange a finite number of particles in a finite volume of space. Infinity will exhaust all of them, and then it will begin again. So what does all this really mean to you? There is a version of this claim that sounds dramatic, but is mostly harmless. But there is also a version that is very difficult to accept. The harmless version? Somewhere in an infinite universe, there is a planet that looks very much like Earth, where a person who looks very much like you is doing something vaguely similar to what you are doing now. That is almost certainly true in an infinite universe, and it is no more threatening than the fact that your name might be shared by someone in another country. But the physicist Max Tegmark, in his 2003 paper on parallel universes, worked out the mathematics more carefully. He estimated that in an infinite ergodic universe, one where matter is distributed without perfect long-range order, an exact copy of our entire Hubble volume, the full sphere of space we can observe, including every star, every planet, and every version of you within it, identical down to the quantum state of every particle, would be found at a distance of approximately 10 to the power of 10 to the power of 29 meters. That number is not a distance you can travel. It is not even a number you can meaningfully picture. It is a number so large that if you tried to write out every digit, the ink alone would outmass the observable universe. And yet, in an infinite space, that distance is nothing. It is just a location, somewhere at that distance, and at that distance again and again, infinitely many times. There is a region of space that is, to every physical standard we know of, identical to ours. Same galaxies arranged the same way, same solar system, same planet, same you. Not a spiritual echo, not a metaphor, but an actual physical arrangement of atoms producing the same electrochemical processes in the same brain, reading or hearing the same words, having the same thought right now. But wait, and here comes the twist this concept always conceals. That copy would not know it is a copy. It would have no reason to suspect it. It would feel exactly as unique, as singular, as irreplaceable as you do now. There is, however, a deeply uncomfortable variant of this idea, known as the Boltzmann brain problem, which we need to address because it reveals something unsettling about how infinity interacts with probability. In a universe that exists for long enough, random quantum fluctuations can, in principle, spontaneously assemble any physical structure, including a fully functional human brain, complete with memories, perceptions, and the sensation of being conscious. Floating alone in empty space, existing for just a fraction of a second before dissolving back into chaos. Physicists, including Andreas Albrecht, Lorenzo Sorbo, Don Page, and others, pointed out that in a sufficiently old or large universe, such Boltzmann brains, random fluctuations that briefly mimic observers, would vastly outnumber the observers who developed through ordinary cosmological evolution. This matters because it asks a genuinely horrifying question. How do you know you are not one? How do you know your memories of a childhood, of relationships, of a continuous life, are not a spontaneous fluctuation that assembled itself a millisecond ago, complete with false history built in? The answer, of course, is that you probably cannot know for certain. But most cosmologists argue that this possibility, while real in principle, points to a flaw in how we set up the probability calculation, rather than a genuine reason to doubt your own existence. We will return to this problem in a moment. First, a philosophical detour. In the year 1686, the German philosopher and mathematician Gottfried Wilhelm Leibniz wrote a short but incendiary treatise called The Discourse on Metaphysics. In it, he articulated what he called the principle of the identity of indiscernibles. Two things that are identical in every possible property are not two things. They are one and the same thing. If Leibniz is right, and this is still a live debate in philosophy, then the idea of an exact copy of you presents an immediate paradox. If the copy is truly identical in every atom, every thought, every memory, every electrochemical state, then in what sense is it a copy? In what sense is it not you? This is not word games. It is a question about what you actually are. If you are your body, the specific atoms arranged in a specific way, then a duplicate arrangement is you, not a copy of you. If you are your memories and experiences, then an identical set of memories and experiences is your identity, and the copy shares it with you entirely. If you are your continuous history, your unbroken chain of causation, then the copy, having an identical history up to this moment, is indistinguishable from you in that respect as well. Leibniz would say, there is no meaningful distinction. His universe left no room for true duplicates, because he believed space itself was relational, defined by the positions of things relative to each other, not an absolute container that could hold two identical somethings at different addresses. Modern physics disagrees with Leibniz about space, but it has not fully resolved what Leibniz was pointing at. What you are precisely remains an open question, and that question, in the context of an infinite universe, is not comfortably abstract. I can already hear the objection forming. You are thinking about quantum mechanics. Quantum mechanics guarantees that no two particles can be in identical quantum states in the same system, due to the Pauli exclusion principle for fermions. And more broadly, quantum processes are genuinely random, not pseudo-random, not determined by hidden variables we have not found yet, but fundamentally, irreducibly random, according to the best physics we have. So how can there be an exact copy of you in an infinite universe, if quantum randomness ensures that every physical history diverges from every other at the subatomic level? It is a fair challenge. And here is its vulnerability. Tegmark's calculation already accounts for this. He is not claiming that your copy followed the same quantum path, event by event, from the Big Bang to this moment. He is claiming something subtler, that in an infinite universe, every possible quantum configuration of matter in a given volume of space exists somewhere, including the exact configuration your body and brain happen to be in right now, at this moment, regardless of how it came about. The path to that configuration might have been entirely different. The end state is what repeats. Think of it this way. If you shuffle an infinite deck of cards, each card representing a distinct quantum state of a given volume of space, every possible arrangement of cards will appear infinitely many times somewhere in the deck. The history of how the cards got into that order does not prevent the order from recurring. The quantum objection, in other words, postpones the repetition. It does not eliminate it. It makes your nearest exact copy farther away than Tegmark's estimate, perhaps incomprehensibly farther. But in an infinite universe, farther away is not the same as non-existent. Let us return to the physics. The Planck satellite launched in 2009 by the European Space Agency, operating until 2013, mapped the cosmic microwave background with extraordinary precision. This is the thermal radiation left over from roughly 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely for the first time. What Planck found? The curvature of space, measured from the small-scale fluctuations in that ancient light, is consistent with zero, with flatness, to an extraordinary degree of precision. The total density of the universe, expressed as a fraction of the critical density required for flatness, is measured at 1.000, plus or minus approximately 0.002. In plain language, space is flat as far as we can measure. And a spatially flat universe that emerged from cosmic inflation is, in the standard mathematical treatment, infinite in extent. We have not proved the universe is infinite. We cannot. Our measurements are bounded by the observable horizon. Beyond that, we genuinely do not know. The universe could be finite, but so much larger than what we can see that no measurement we could ever make would detect the difference. Some theoretical models, particularly those involving non-trivial cosmic topology, allow for a finite universe that looks flat locally. The detection of such topology is an active and unresolved research question, but here is what we can say. The infinite universe is not exotic speculation. It is the default, simplest reading of our best current cosmological data. It is not ruled out. It is, in fact, favored. In an infinite universe, the concept of probability becomes deeply problematic. If every possible configuration of matter exists infinitely many times, then the question, how likely is it that I am in this particular configuration, becomes formally undefined. You are dividing infinity by infinity, and mathematics does not have a clean answer for that. This is not a philosophical quibble. It is a real crisis that sits at the center of inflationary cosmology, the very model that predicts the flatness and probable infinity we just discussed. The Boltzmann brain problem I mentioned earlier is one symptom of this crisis. If we cannot correctly weight observers in an infinite universe, we cannot make reliable predictions about what a typical observer should expect to see. And if we cannot do that, we cannot meaningfully test the theory. Physicists like Tegmark, Alexander Vilenkin, Andre Linde, and others have spent decades trying to construct a valid measure, a consistent way to count, or weight, or compare the infinitely many observers in an infinite universe. So far, no solution commands consensus. Every proposed measure either produces paradoxes or makes predictions that conflict with observation, or involves assumptions that cannot be justified from first principles. This is the honest state of affairs. The infinite universe, and the copies it implies, lives at the frontier of what we know, not in the comfortable interior of settled science. It is a prediction that flows naturally from our best model of the early universe, and yet one that we cannot fully formalize, cannot test directly, and cannot quite escape. So, let us return to Campo de Fiori. The bronze figure stands there still, hooded, looking down, not at the ground, but somehow inward. He was burned for a cosmology, for the audacity of saying, this is not the only world. Space does not end at the edge of the known. He was wrong about many things. He was a mystic, not a physicist, and he had no mathematics to support what he felt to be true. But on the essential point, that the universe does not arrange itself for our convenience, that it does not end at the boundary of our vision, that somewhere beyond what we can see, there are other arrangements of matter going through their own versions of what we go through. The equations we have built over 4 centuries of science have not contradicted him. The copy of you, at a distance whose digits would overflow every book ever written, is right now having the thought that you are having, feeling what you feel, perhaps wondering, as you are, what it means. Bruno looked up at the stars and saw infinite worlds. We look at the mathematics and see infinite copies of ourselves, separated by distances language barely has words for.